Can you hear me online? All good? Okay. Yeah, we have 4 minutes, so. Okay. I think we have thin attendance today, probably because of the holidays coming up tomorrow, I assume, or the bad weather. I don't know. Okay. Welcome to lecture 17. We're going to study two important paradigms today that are actually used in modern computers. One is a very general purpose paradigm, as you will see, very long instruction word architectures. It's a very principled approach to design computers by making the software complex and hardware simple, or the other way around if you want to think about it. Make the hardware as simple as possible. Software does all the heavy lifting to get the high performance, which is a very different approach than what we did with out-of-order execution. Right? In out-of-order execution, we said software stays as is. We're going to accelerate everything in hardware, right? By scheduling instructions out of order. Here, the software will be responsible for doing the scheduling of instructions and hardware doing none of that. And then we're going to talk about systolic arrays, which is really the base of many machine learning accelerators today. So hopefully it'll be exciting. Okay, so VLIW architectures. So this is where we are. We are covering a lot of microarchitecture, but today actually we're going to cover not just microarchitecture, but also some hardware-software interface, which is the execution model. And we've covered a lot of approaches to getting more concurrency out of programs. And I'm going to start actually by giving an overview of superscalar execution, because superscalar execution is a paradigm that's very hardware-oriented. VLIW is going to be a paradigm that's very software-oriented. I'm going to contrast. If you remember, this is a slide that we used in lecture 15A, and we discussed the idea of superscalar execution. It's a very basic concept. The idea is to fetch, decode, execute, and finish or retire multiple instructions per cycle, as opposed to doing it for one instruction per cycle, do many instructions per cycle. And we said that today, many processors are 8 instructions per cycle. But of course, to be able to do this, you need to have the hardware resources. You need to have the hardware resources to concurrently fetch, decode, execute, retire 8 instructions per cycle, let's say. And you also need to, in hardware, do dependence checking across those concurrently fetched instructions. Remember, we were doing dependence checking horizontally in the pipeline if you have single instruction, if you're fetching, decoding, executing single instruction. If you're fetching, decoding, executing multiple instructions in a given cycle, you need to also do dependence checking vertically. So dependence checking needs to happen both horizontally in the pipeline and also vertically in the same cycle, which makes the design much more complex. Today, we're going to have a solution to it with a different paradigm. But these are also slides that you have seen in lecture 15A. Basically, to be able to execute or fetch multiple instructions per cycle, we need to essentially have a mechanism to fetch multiple instructions per cycle, decode, and access the register file for multiple instructions. Here, you're seeing only 2 instructions. ALUs, enough ALUs to execute concurrently multiple instructions per cycle, enough force to memory, etc. But of course, dependencies make it tricky. You need to detect dependencies between concurrently fetched instructions and delay the instructions whose data values are not ready. So we are very familiar with all of these concepts. And superscalar processor makes it harder because you need to detect dependencies. But if there are no dependencies between concurrently fetched instructions, as you can see over here, this add is not dependent on load, this AND is not dependent on sub, this store is not dependent on OR, then you can get 2 instructions per cycle. That sounds good. But we also saw an example where there were some dependencies between instructions, as you can see. As a result, you are not able to, let's say, finish 2 instructions per cycle, and your instructions per cycle can go down significantly in this particular case. And then I also asked the question in that lecture, can you do better? Can you reorder the instructions to actually improve the performance that you get out of a superscalar machine? And the answer was yes, if the programmer or the compiler can do that reordering such that independent instructions go in the same cycle, then you can actually achieve the benefits of a superscalar processor. But the hardware still needs to be there, meaning the hardware still needs to do dependence checking, both horizontally in the pipeline as well as vertically in the same cycle. And that's expensive, essentially. So that is all review. Now, what is VLIW architectures? Essentially, the concept is very different from superscalar. It's trying to achieve the same thing. But essentially, in superscalar, we did everything in hardware. We fetched multiple instructions per cycle and checked the dependencies between them. And hardware was doing the tough job of actually doing all of that. In VLIW, the approaches put that burden on the software. Essentially, software, it could be the programmer, but hopefully the compiler, packs independent instructions in a larger instruction bundle together, called a very long instruction word, essentially, such that they are fetched and executed concurrently so that hardware does nothing. Nothing in terms of dependence checking. Software guarantees that instructions that are fetched in the same cycle are going to be independent of each other. That sounds good, right? That would be ideally great, but we're going to see the downsides of it also. So hardware fetches and executes the instructions in the bundle concurrently, essentially. So essentially, this is not only done in the pure VLIW model. You don't do it just vertically, but you also do it across the pipeline stages, meaning horizontally in the pipeline, such that hardware doesn't need to have any dependency checking. You eliminate dependence checking hardware. You put that burden to the software. So software exactly knows the microarchitectural structure of the pipeline. It knows there are so many stages. It knows how many cycles each instruction takes. It knows how many instructions the hardware is capable of fetching concurrently, and does all the dependence checking, instruction scheduling in those pipeline slots. That sounds like a beautiful model, if it works, of course, right? So the idea is hardware is simple. It doesn't do complex things. Software is complex. It does all the code scheduling to keep the pipeline full and fully utilized, both at the horizontal and the vertical dimensions. So this is the philosophy. Simple hardware, complex compiler. Very different from what we have seen so far. This is why this is one of the reasons this is actually a very interesting and important paradigm. The big things come when people think differently. If everybody is thinking the same, big things will not happen. Here's an example of big things happening when someone thinks differently from others. Okay, so this is my pictorial depiction of how this works. Essentially, what you do is you have a program counter. It is still a sequential execution model. Once you get to that program counter really encodes multiple operations. So you cannot address these individual operations individually. Whenever you get to a program counter, you fetch a very long instruction word that contains multiple operations. In this case, 4 operations: add, load, move, multiply. And you fetch them. Compiler guaranteed them that they're independent of each other. There's no dependence between them because compiler did the analysis of the code and reordered things. And then basically you fetch them and you directly supply them to the processing elements. That sounds beautiful, right? Now there's also something else. Processing elements compiler also knows which processing element is where, such that it knows that this, let's say this processing element is capable of executing load instructions, but none of the other ones is capable of that. It could be possible. The processing elements don't need to be heterogeneous. They can be don't need to be homogeneous. They can be heterogeneous. Then the compiler knows I can put a load only in this position in the instruction, so that when the hardware fetches it, it directly has a wire and routes the load to that location, as opposed to having some sort of shuffling network where you need to shuffle instructions from one location where you fetched it from to the processing element that may be far away. So hardware actually gets simplified for multiple reasons, as you can see, not just dependency checking, but if you actually expose the structure of the pipeline, where are the processing elements, assuming they're all they have differences between them, then the compiler can actually help you reduce the hardware cost. And this model was introduced in this beautiful paper, Very Long Instruction Word Architectures, and the ELI stands for Enormously Long Word Instructions, 512. And it was 512 because this was 512 bits. So far, we've been talking about 32-bit instructions, right, in MIPS. This is 512 bits. So if you think about a MIPS instruction, this could be 8 no, not 8, right? Is it 16? 16 instructions, yes. And we're going to see people have tried to design machines that can concurrently do 28 instructions, for example. It's beautiful. You can exploit parallelism very nicely. And hardware doesn't become complex. Okay, so let's go into a little bit more detail. I gave you the key idea. The rest is detail and also a little bit analysis and also a little bit history. I'm going to give you a lot of history of this paradigm. We thought this paradigm was not working, but it is actually used in modern machine learning accelerators today also to supply work to some other units. So a lot of the paradigms we study are used in different ways today, and it's actually quite powerful. Okay, so basically you have a very long instruction word that consists of multiple instructions packed together by the compiler. Again, anything compiler can do, this programmer can do also. You can do it yourself if you have a VLIW machine, but it's very tough for the programmer, of course, right? You need to do all the analysis that the compiler should do. So packed instructions can be logically completely unrelated. You will see what this means when we actually talk about SIMD vector processors or GPUs next week, or not next week, next week. You can rename next week to next week whenever I say that, because clearly next week we don't have lectures. But basically, in that case, in a GPU, for example, or vector processor, the instructions are the same. You fetch one instruction, but you actually encode many operations on different data elements. Here, the instructions are very flexible. It could be very different from each other. So the idea is to have the compiler to find the independent instructions and statically schedule them, or pack them, or bundle them into a single VLIW instruction in the same single cycle, and also do it across multiple cycles such that the pipeline is completely full so that you don't need any dependence checking. So traditional or purist VLIW characteristics are like this. You have multiple instructions: fetch, decode, execute, retire. You have multiple functional units. So hardware becomes complex from that perspective. But hardware is simple because there is no dependency checking. All instructions in a bundle are executed in lockstep, meaning if all of the instructions are kind of scheduled such that they finish at the same time, if possible. We're going to see that this is going to be very difficult with memory instructions. When you do a load, for example, if you have one load in the bundle, that may need to wait because it may take a long time, right? So when that needs to wait, all of the instructions need to wait. So you stall the entire pipeline. And this is going to be one of the big downsides of this paradigm. And as I said earlier, instructions in a bundle are statically aligned so that they can be directly supplied to the functional unit so that you don't need to route the instructions from one place to another. We already discussed that earlier with the picture. So let's take a look at what these bundles look like. So again, this is actually a very similar code to the Superscalar code that we have seen earlier. What the compiler does is compiler analyzes the code and make sure that instructions in a bundle are independent of each other. So this add is not dependent on load. That's bundle 1. This AND is not dependent on sub. That's bundle 2. And this store word is not dependent on OR. That's bundle 3. The compiler also does it between instructions such that, for example, an instruction doesn't depend on this load. Because if you remember in the pipeline structure that we have seen, if there's an instruction in the bundle 2 that's dependent on the load over here, you cannot, you need to have a stall, right? Because you cannot forward the data value. There's this load stall that you need to obey, which we discussed when we discussed pipelining. So the compiler makes sure that the instructions that come after a bundle where there's a load are not dependent on the load, for example. So compiler needs to actually do the scheduling both horizontally and vertically. So this is how the instructions get executed. And in this case, there are no dependencies. That sounds good. So you get ideal IPC, which is 2. The question, of course, is what if the compiler cannot find an instruction to put in a bundle because there are a lot of dependencies in the code, or the compiler was not good enough in its analysis, etc. Then you basically had a no operation, right? No op, which means that you waste some of your utilization, potential utilization of the pipeline. And this is going to be another issue with this paradigm. So one issue is if this load needs to wait for longer, because load latency, as we will see later in the memory lectures, load latency can be very long. If you hit in the cache, as we will see in caching later, it could be 1 cycle. But if you miss in the cache, it could be 100 cycles. The compiler doesn't know whether a load, whenever it generates the address, the data will be in the cache or not, right? So the compiler schedules the instructions assuming that it hits in the cache, but when you execute it, if it misses in the cache, then that bundle will wait for 100 cycles, okay? And this is going to be the difficulty in dealing with instructions this way, because compiler does everything. Hardware cannot do anything. Whereas if you remember in the out-of-order execution model, that load waits, but other instructions can be fetched and executed, right? Here you stop. That bundle stops, so no one else can get executed. Okay, that's the downside of static scheduling. So I'm giving you the downside and upsides, as you can see. We're going to summarize them later. Okay, so basically that's what I said. Lockstep, all or none execution. If any operation in a VLIW instruction stalls, all concurrent operations stall. No later operations can continue in the pipeline. Why? To keep the hardware simple. This is exactly the opposite of out-of-order execution. Out-of-order execution, when someone stalls, there are other instructions you can try to find and execute, right? That sounds good, but there is a trade-off here. So in a truly VLIW machine, the compiler handles all data dependence related stalls, as we've discussed. Hardware doesn't perform any dependency checking, ideally. But unfortunately, if you have a variable latency operation like a load, sometimes you hit in the cache, it's 1 cycle. Sometimes you miss in the cache, it's 40 cycles. Sometimes you have to go to memory, it's 100 cycles. Loads are actually very problematic in modern machines, as we will see in the memory hierarchy lectures. You cannot know, essentially, how long an instruction will take, so it's very difficult to schedule things. So that's going to be the Achilles heel of this. So in codes where you can analyze really well, fit into your cache, this paradigm works really well. That's one of the reasons it's actually employed nicely in some cases when you do matrix vector multiplication, for example, in modern machine learning workloads, because you can analyze some of those codes really, really well. Okay, so I'll also talk about some history. Josh Fisher was the main person who developed this idea. And you can see the title of one of his papers, like Parallel Processing, a Smart Compiler and a Dumb Machine. Very different from what other people were doing at the time. So philosophy is actually somewhat similar to reduced instruction set computers that we had discussed. We discussed that instruction set complexity is something that you need to consider when you actually design an instruction set architecture. If your instructions are complex, your hardware becomes complex because you need to execute them. If your instructions are simple, your hardware becomes also simple, right? In a sense, VLIW philosophy is very similar to that RISC philosophy. So let's talk about that. Except VLIW adds multiple instructions in parallel as well. Okay, I don't know. Anyway, I don't want to deal with it right now. There's some thing over here that I'm going to later fix. But RISC philosophy was initially developed by IBM, John Cock, who's a Turing Award winner, actually. He basically said, compiler should do the hard work to translate high-level language to simple instructions, ideally control signals. Compiler basically translated an instruction to control signals. And of course, the compiler should also reorder simple instructions for high performance. So RISC processors have a similar philosophy. Hardware does little translation or decoding. As a result, hardware is very simple. VLIW essentially takes it to the next level. We also want to fetch and execute multiple instructions. So in the vertical dimension, compiler does the hard work to find instruction level parallelism as well. Hardware stays, again, as simple as possible. Each instruction in a bundle executes in a lockstep. So these two things are actually similar to each other, and they have had a lot of influence in the field, clearly. So why do we want to keep hardware simple? This is kind of obvious, but let's reiterate. Because if you have very simple hardware, it's easier to design. It's easier to verify. Today, actually, verification costs of a modern processor is a lot of the time, 60% of the cost, maybe more than 60%, 70% of the cost is verifying that it works correctly. Right? People design the processor, implement it, and eventually they need to do a lot of testing, both online and offline, to make sure it works, and that's actually very costly. So if you have a very simple processor, it's a lot easier to verify, easier to design. It's also low power, hopefully. It's also higher frequency. You can make the frequency very high, right? Okay, so this is from Josh Fisher's paper. I think I've said everything over here, but maybe to say that each operation in a bundle requires a small, statically predictable number of cycles to execute. So this is good to think about. Statically predictable means whenever you're doing compiler, you know how long the instruction takes. That's not the case, unfortunately, for especially memory instructions. But that's also not the case for some other instructions if you do some optimization. For example, I'll take a multiply instruction. Does a multiply instruction always take n cycles? Let's say n is 8 cycles, I just picked. Basically, the answer is depends today. Why? Because if you're multiplying by 0, you can have a shortcut in the circuit that says, oh, the answer is 0 because one of the operands is 0. You could do it in 1 cycle with an equality checker. So sometimes a multiply takes 1 cycle, sometimes a multiply takes 8 cycles, depending on the data value. The question now becomes, is this statically predictable? Can the compiler predict whether a multiply is going to take 1 cycle or 8 cycles? Probably not. Compiler needs to analyze the data values. If the data value is predictable, that's good, absolutely. But if the compiler doesn't know the data values, which is the common case, then the compiler cannot do anything. Right? It cannot statically predict it, essentially. It will basically need to say, okay, it will basically need to assume something. If it assumes 1 cycle, then it basically schedules the dependent instructions after 1 cycle. But then it's assuming that multiply is always operating with an operand of 0, which is probably not a good assumption, right? If it assumes 8 cycles, when the multiply has an operand of 0, it did all the hard work and it didn't really yield any benefit. So that's the difficulty, basically, when you do scheduling at the compiler level. You don't know the latencies of all instructions. And especially load instructions are the culprits. Okay, let me give you some history also. So Josh Fisher actually developed this idea, and then he basically went up and started his company, and he built 7-white, 28-white VLIW processors. Bob Rao was doing similar things at the same time, and he built his own company. These are actually very early competitors, let's say, to complex processors at the time. At the time, the complex processors were similar to x86, like VAX. It was one of the complicated and top-notch processor. And later, Transmeta Crusoe, which we mentioned earlier, it basically had an idea. Oh, I want to execute complex code, but I want to actually have a very simple hardware. So I'm going to translate the x86 binaries to internal VLIW processors. Now you know what that VLIW means, right? You have a software translator that optimizes the code, that figures out how to turn that x86 binary into a VLIW processor such that the hardware stays simple, software is complex. This is ISA translation that we've seen. We're going to look at that later. And later, actually, people have designed digital signal processors and embedded processors. And these were the most successful commercially until the latest machine learning accelerators, let's say. And these folks actually did embedded processing, and a lot of the code over there is relatively statically predictable. That's one of the reasons they were successful. Intel actually also had an innovative project in the 1990s. They basically when they were moving from 32-bit x86 to 64-bit x86, they also wanted to change a lot of things in the instruction set architecture. They wanted to move to a VLIW type of engine, but they said this was not fully VLIW. It was based on some of the VLIW principles. In fact, it violated the most important one. In a bundle, you could specify dependencies. So the compiler can put dependent things in a bundle, but the compiler says, oh, this instruction is dependent on this instruction, because compiler can do some of that analysis clearly, right? So this simplifies the hardware, because hardware doesn't need to check the dependencies because the compiler is telling them, but it's not perfect VLIW in the sense that not all instructions in a bundle are independent of each other. So Intel actually tried hard on this one. So how do they encode dependencies? A few bits in the instruction format specifies explicitly which instructions in the bundle are dependent on which other ones. So again, I will not go through this, but this was actually something Intel pushed a lot. But unfortunately, it was very difficult to move the software world to this sort of paradigm. As a result, Intel had to abandon this, even though it was a very innovative project to change the nature of x86, let's say. Okay, so that's some history. We're going to see a little bit more history, but let's talk about the trade-offs. I think these are actually hopefully clear. There's no need for dynamic scheduling hardware, so you have simple hardware. This is an advantage, clearly. No need for dependence checking in a VLIW instruction. You have simple hardware for multiple instructions, no renaming. All of that hardware complexity goes away. No need for instruction alignment after fetch to different functional units. Simple hardware. Basically, advanced are all simple hardware, as you can see, right? And simple hardware, in turn, has benefits that we discussed. Disadvantages, now the burden is on the compiler, complex compiler, essentially. A compiler needs to find n independent operations per cycle. Not only that, actually schedule the operations inside the pipeline also, so that the pipeline doesn't stall. And if it cannot do that at any point, at any slot, it has to insert a no-op. So basically, there are a lot of no-ops in a VLIW instruction when the compiler is not successful. And there are many workloads where the compiler is not successful, because compiler doesn't have perfect knowledge about what's happening dynamically. So if you have no-ops in an instruction, you lose parallelism. And then code size also increases because you need to encode no-ops now, right? You need to encode all of the operations that the program needs to do plus no-ops, right? So if you add 100% no-ops, your program size becomes double, right? And if your code size increases, then you have other issues like now your caches need to become larger, or you get more cache misses, etc. So there are a lot of issues. You don't want larger code size. There's another disadvantage. Because your compiler is so tightly coupled with the microarchitecture. In fact, now the microarchitecture itself is what the compiler is optimizing directly for. Whenever you change the microarchitecture, your compiler needs to change also. And this could be any small thing in the microarchitecture also, right? You change a latency here, you change another latency there, and the compiler, what the compiler did may not be very good for performance. Right? So as your execution width, instruction latencies, and functional units change, you need to recompile code to get the best performance, or even to be correct in some cases, right? Potentially. So this is very different from superscalar processing, which is completely transparent to software, right? You don't need to do anything in superscalar processing. And if you do out of order on top of superscalar, you schedule the instructions dynamically, and as a result, you can get good parallelism as well. Okay, and then the lockstep execution. This caused independent operations to stall. As we discussed. As a result, no instruction can progress until the longest latency instruction a bundle completes. And if that's a load, you're in trouble, because the load may be taking hundreds of cycles. Okay, so these are actually the big disadvantages that unfortunately hurt VLIW paradigm. And as a result, it wasn't successful in the general purpose domain. So today you don't see a lot of general purpose processors that are VLIW. All of them are out of order superscalar. But in other domains, it was very useful. And we will see what those are quickly. So essentially, you simplify hardware, but you require complex compiler techniques. And the solely compiler approach of VLIW has several downsides that reduce performance. No tolerance for variable or long latency operations. Loads. And loads are extremely important, as we will see when we talk about the memory lectures. Most of the execution time of modern processors is spent on accessing memory. If you don't handle loads well, if you cannot tolerate their latencies well, your performance will tank. Okay. And then there are too many no-ops. In many workloads, it turned out that you have a 28-wide machine, for example. Maybe you have 4 IPC. So your machine is huge, but you're not getting enough parallelism because you cannot, most of those instruction slots are used for no-ops. And then the static schedule is intimately tied to microarchitecture, meaning code optimized for one generation can perform poorly for next. Even though the machine improves, if you don't recompile your code, meaning if you don't spend time on your compiler to do a better job, your machine will not be utilized well. This is again very different from improving your, let's say, increasing your instruction window size and out of order execution. Right? Immediately you get benefits, hopefully. Right? Whereas here, you need to recompile the code. Okay, so these are the downsides that made VLIW not commercially successful in the general purpose domain. But the huge upside, that's why there we have 2 pluses over here. Everything is downsides and upsides. Okay, most compiler optimizations that are developed for VLIW are used today. So if you're using a compiler, thank VLIW paradigm. Because those are the optimizations that were enabled and went into all of the processors because people said, yes, these are designed for VLIW, but it's good for Superscalar as well. So people adopted all of those compiler optimizations. And the beautiful compiler optimization, I'm going to show you a couple of them. And they not only improve parallelism, but enable other code optimizations as well. So by scheduling code in an intelligent way and ignoring some, let's say, not commonly executed code, you can do optimizations across commonly, ignoring uncommonly executed codes, you can do optimization across a commonly executed path. So you can actually reduce the complexity of frequently executed parts of a program. And this is what's employed in dynamic compilers, but also a lot of static compilers today as well. So you're going to see some of the dynamic compilers that I kind of threw at you in earlier lectures, but hopefully they'll become a little bit more clear this way. And then there's also another plus. VLIW is actually a very successful paradigm when parallelism is easier to find by the compiler. As a result, in some limited special purpose domain like embedded markets, digital signal processors, in some GPUs, early GPUs, and more recently in machine learning accelerators, where you can actually analyze the code nicely and you can statically predict some things, you can actually get benefit from VLIW. Make sense? Okay, so let me give you an example of these compiler optimizations, because this is really the big benefit of VLIW that's generally employed essentially without many of you knowing it perhaps, or many people even using compilers not knowing it potentially. People who are developing compilers know it, of course. But basically, this is an example again from Josh Fisher's seminal paper. These are basic blocks, you can see. A basic block is essentially a piece of code with potentially multiple entries and multiple exits, right? It ends in a branch. You enter the basic block and you branch out and you go to another basic block. This is a control flow graph of the code. It looks like a mess initially. But if you profile this code at compile time or dynamically, maybe you figure out that, oh, this is the path I usually take in the program. This is a frequently executed path, okay? So if you identify that, this paper also introduced trace scheduling. Another paper introduced trace scheduling before this for other reasons actually, but for VLIW it works really well. The idea is basically you find out the frequently executed path. How do you find out? This branch is 99% going this way. This branch is 99% going this way, 99% this way, 99% this way, 99% this way. So probably you're going to execute this code very frequently, dynamically, assuming your profile is representative. Let's assume that. Now what you can do is you can optimize the code along this path, meaning cut the connections. You cannot exit from here. When you enter this code, you can exit from some places perhaps, but essentially you look at this, the set of basic blocks in unison as if they're going to execute in this path. You optimize the code and you do some things that would be incorrect if you actually got out of this control flow graph in dynamic execution, and you make up code for it. Essentially, you optimize the code as if this is going to execute in unison, but you also add exceptions. If that's not the case in dynamic execution, you take the branch, for example, outside, you add some makeup code that undoes things that you think that you did because you thought the code was going to execute in unison. Makes sense, right? So this increases the code size because you need to add a lot of this makeup code. This is actually called makeup code. You basically make up what you've done. Undo code also. Undo blocks. You actually undo what you did that you shouldn't have done. Hopefully that makes sense, right? So now your code is really optimized for this path, but it's also correct. If you actually get out of this path, you can get out of it, but now you have to pay the penalty of undoing stuff that you did you shouldn't have done. Okay? So that's a beautiful idea. It's called trace scheduling. And this is the basis of a lot of compiler optimizations. Compiler optimizations can be done without this, but this enables compiler optimizations And the main reason is you don't need to consider branches. So a lot of compiler optimizations are hindered because, okay, you want to move some code from here to here, but there's a branch there. I cannot move that code, right? If that branch goes that way, yes, I can move it. But now I'm assuming that branch goes that way, so I can move code freely within that block, right? So this makes the compiler very powerful. Okay, so that's this is why this paper is very recommended. Even though we don't talk a lot about compilers in this course, this is actually the really basis of modern optimizing compilers. Okay, we have seen some of this compiler optimizations before, like basic block reordering, if you remember, right? We reordered basic blocks when you discussed basic block reordering. We reordered basic blocks such that the not taken branch prediction is good, right? Is effective. It's kind of similar to that, right? Except in this case, we're relying on branch prediction. So if the branch is executed such that you mispredicted, you flush the pipeline. Right? Here, instead of flushing the pipeline, you're relying on the compiler. If you actually go out, you do some other stuff to undo what you shouldn't have done. Okay? Okay, so let me give you one other idea. There are a lot of ideas. This is a very important paper also. It was published in 1993 by Wenmei Hu's group. Essentially, there's a problem with trace scheduling that hinders code optimization. You can do better, essentially. People always ask, can we do better in compilers? So we've seen a lot of hardware, can we do better? Let's see a compiler, can we do better? One of the problems with trace is you have a single entry, but you have multiple exits over here. Okay, sorry. You can have multiple entries, multiple exits. So you can basically enter the trace from somewhere here, and you can exit the trace anywhere. So it's multiple entry, multiple exit, which actually hinders some of the compiler optimizations. But Superblock says that we can combine frequently executed blocks such that they form a single entry, multiple exit larger block, which is likely executed as straight line code. Basically, you cannot enter from somewhere else. So if you look at this, it's a trace, and you exit, and then you can enter again. And you optimize this path. But the optimization of the path is hindered by this entry into the code. Superblock says, once you enter this thing, you're not going to enter from somewhere else again. You can exit, but you're not going to enter. So this reduces actually branch mispredictions very well. I'll not go through that. It enables aggressive compiler optimization and code reordering within this Superblock. Of course, the downsides are increased code size, more recompilation, and profile dependence. Let me give you an example. So this is our messy control flow graph. Each of these end with a branch, and these are the probabilities of which way the branch goes. So after A, 90% of the time the branch goes to B, 10% of the time you go to C. Okay, so essentially you figure out what is the frequently executed path. And this is the frequently executed path. And then you identify this trace. Now this is a kind of a trace, a frequently executed path. And you have the probabilities over here, as you can see, 90, 90, 90. 90 is a low probability, by the way. Ideally, you would like to get to higher. But that's okay, this is a trace. It has multiple entry points. You could enter from here, for example, enter from here. And then it has multiple exit points. You could exit from here, here, and then you could, of course, enter from here at the top. Now, we want to eliminate the side entries. Basically, when we exit the trace, we don't want to enter it again, okay? Or we don't want to enter the trace anywhere in between. We just want to enter it from the top and execute that straight line code. And we can enable a lot of optimizations because there's no incoming branches. To be able to do that, this work introduces what's called a tail duplication. It basically duplicates the basic blocks after a side entrance. So remember, there's a side entrance over here. There's another side entrance over here. And then they both execute F afterwards. So why don't you actually have another copy of F such that these, whenever you enter this code, you don't enter the trace again. You basically go to some other place in the code and execute another copy of F. That's the idea, basically. Essentially, this transforms the trace into what is called a superblock in this work. Now this is a superblock, meaning, I don't know, you can take issue with the name, but that's what the people named, and that's what everybody uses today. Essentially, you have a code with a single entry point and multiple exit points, but you cannot enter anywhere other than the top. Now, this enables a lot of code optimizations internally, as that paper showed. Let me give you one example. So this is my, I ignore a lot of the branches. I just look at the operations over here, right? The first operation is multiplying R2 and 3, putting into R1. And then 99% of the time, you go to this multiply. Essentially, you do the same thing if you realize. But 1% of the time, you increment R2 by 1. So you should go this way 1% of the time. Okay, so if you do a superblock formation, this is what you do. You form a trace, you eliminate the side entry here, meaning you duplicate this one, put it, if you exit from here 1% of the time, you execute this, and you also execute a copy of this, so that you don't enter back. Now, once you eliminated that enter back, this code, you can reduce the strength of this operation. Why? Because you already calculated it. Here, right? These multiplies are the same. The realization is that you can eliminate, you can basically identify the common sub-expression. This is called common sub-expression elimination. R2 times 3 is a common sub-expression between these two operations. They're both doing R2 times 3. So you realize that this already computed R2 times 3, so I'm just going to move R1 to R3 for this. So I reduce the strength of a multiply to a move, and moves are much cheaper than multiplies, okay? So even this 3 instruction code, which is very beautiful, I think, demonstrates the power of optimization. This couldn't have been done if you entered back, right? If you actually didn't duplicate this multiply instruction over here, if you actually did the add and entered back, you couldn't do this optimization because you don't know which one to use, right? So you can see now the power of optimization, right? And this is, apply this to a large block, it becomes actually much more powerful. Okay, so if you're interested, this is the paper on Superblock formation, and we have some lectures on static instruction scheduling that are old. Wen-Mei Hu's group did a lot of work on optimizing compilers, and they're responsible actually for a lot of improvements in compilation. They're also responsible for convincing Intel to do IA64 in parts, which was a great experiment, but it didn't pan out well. But that's what researchers are for. That's what progress is for, right? You got to do experiments and sometimes fail. I mean, most of the time fail. And it didn't fail, I think. Okay, so there are also hyperblocks if you're interested, but I'm not going to talk about that. So people actually kept improving these things. There's more on top of this. This was an early compiler, so people actually worked on compilers. This is Josh Fisher's student, John Ellis, when Josh Fisher was a professor at Yale University, before he said, I'm going to do my startup and do a lot of good things, let's say. He basically, his group designed this compiler. So a lot of the optimizations in a compiler actually goes to memory, essentially identifying which instructions are independent of memory operations, which memory operations are independent of each other. So memory becomes a huge problem, essentially. So if you look at all of these compilers that are developed, a lot of the time is spent on identifying which memory operations are dependent on each other, which memory operations are how long latency potentially. So that's why we're going to talk a lot about memory later on. Figuring this out in a compiler is very, very tough. And that's one of the difficulties of VLIW in general. It cannot handle variable latency or memory operations very well. Okay, so there are lectures over here, and this is a compact version. Now, let me, I think we still have, good, a couple of minutes, and you can also ask questions if you have questions. But basically, ISA, I'm going back to ISA translation. So what we're talking about is an ISA, actually. VLIW is an ISA, and also a microarchitecture. It's really a paradigm of execution. Right? You don't, out-of-order execution, for example, is not an ISA. Right? It's a paradigm of execution, but it's hidden. It doesn't touch the ISA. Right? Here, we're touching the ISA and the hardware. We're across the stack and the compiler in the end. So if you can do that, you can actually do a lot of ISA translation, and you can get some of the benefits of the VLIW without having the downsides potentially. Right? And people have tried that. Essentially, you can have a program, this is actually an old slide also from another lectures. You can have programmable visible ISA, a virtual ISA, and you can convert it to implementation ISA. You can convert complex instructions to simple instructions as current processors do, as we've discussed, right? Or you can actually start with a scalar ISA like x86 and convert it to a VLIW ISA. So we've seen earlier that Intel's and AMD's x86 implementations translate x86 instructions into programmer invisible micro operations in hardware, right? So that's one sort of ISA translation completed on hardware, so such that the difficult instructions make, you don't need to implement them directly in hardware. You can actually convert them to simpler instructions in hardware. So that makes the hardware simple by adding more hardware. That makes part of the hardware simple. Okay, but what else you can do? You can actually take x86, a complicated ISA, and translate them to some secret, more open source, it doesn't matter, but secret so that if you want to make a lot of money, let's say, secret VLIW instructions software. So that's what Transmeta did. So there are trade-offs over here, of course, that some of which we discussed. So this is what I showed you in the past a little bit, but now this makes a lot of sense. These folks said, basically, we're going to compete with the best x86 processors at the time. Again, these are very motivated folks. We're going to design the best system at the time, but we have a very different idea. We're not going to do things in hardware. We're going to take x86 code. We're going to design some software that can translate it with a lot of code optimizations. All of the code optimizations that we talked about and many we didn't talk about, that's the code morphing software. And it's going to spit out VLIW instructions, and our hardware is going to be very simple and beautiful. So we can design this hardware extremely fast, and we're good software designers, so we're going to design the code morphing software fast also, and then we're going to compete with x86. And this was actually a pretty interesting competitor. Unfortunately, it didn't pan out also, because this software has a lot of overhead, and also it has a lot of the downsides that we talked about. But they did actually produce processors, and in the end, they were power efficient, but not necessarily very high performance. But again, this picture that I showed you in the past, people actually do it in real life. So this is the transmit approach essentially. You take x86 and translate it to VLIW. In this case, they used a software translator, which was actually very efficient, but not necessarily high performance. Okay, if you're interested in this, there's a beautiful paper, white paper by Transmeta, Alex Kleiber, who developed a lot of their compiler technology, wrote this white paper, and that talks about a lot of the code optimizations that they do, and a lot of the support that they added to the hardware so that they can actually get the code optimizations to be very high performance. So what has been successful, more successful, let's say, is a bigger company doing this internally without competing with anyone, let's say. So this dynamic binary translator is essentially a code optimizer. It basically translates x86 to some internal ARM instruction, not VLIW necessarily, but it does actually a lot of code optimization also. So a lot of companies internally do it. Sometimes they write papers about it. So that's Apple. NVIDIA actually does that also. So these code optimizations that we discussed, they are done in those code optimizers, basically. You can see that, there are instructions, and you go into an optimizer. That optimizer is actually software, and it's using a lot of the concepts that are developed by VLIW processors. Some of them actually have hardware support as well internally. Okay, but if you read, for example, here, co-designing a hardware processor with a dynamic code optimization software system creates both additional validation exposure and benefits. The DCO system can be upgraded in the field to address functionality, performance, or security issues. This is a very nice summary of what a dynamic code optimizer can do for you. You can actually upgrade in the field also. But again, keep in mind that if all of that push for VLIW didn't exist, it was going to be very difficult to develop those compiler techniques as quickly as possible. So even though VLIW paradigm may not be the dominant paradigm today, it has had a whole lot of influence in real systems. And its influence is going to continue, as we will see in the next lecture. So again, we are talking about ISAs. This is a lecture that's kind of out of place, but we're also talking about execution paradigms. Once you're talking about execution paradigms, some execution paradigms really span across the stack. So VLIW is one of them. Systolic array is going to be another one of them, as you will see soon, but it's going to be a completely different one. Okay, there's more lectures if you're really interested. But if you're not interested, you don't need to look at them. Okay, any questions? We're done with VLIW. Yes, please.
Wouldn't another benefit be if we saw the example where the instructions were the same, but if they were different but very similar, we could just vectorize them and vector operation.
So yes, in the compiler, you can detect some of those, and you can do vectorization. Yes, we're going to talk more about that when we talk about GPUs. But yes, an intelligent compiler can figure out how you can vectorize operations as well. Okay, I think let's come back when the bell rings, and then we're going to talk about systolic architectures. See you. Okay, let's see. Okay, I think let's get started. Before we move to systolic array architectures, I should mention one thing, because everything we discussed earlier, like compiler doing optimizations, we were looking at, for example, how often is this branch taken or not taken? How does the compiler know that information? It profiles the code, essentially. It puts some input data and basically checks based on some input data sets, what fraction of the time branch goes taken or not taken. So clearly these optimizations are dependent on how good your profiling data sets are, right? So keep that in mind. We discussed this earlier. When we do any static code optimization, you're dependent on the input or profile guided optimization. You're dependent on the goodness or representativeness of the profile input set. So keep this in mind. A lot of these optimizations are dependent on profiling, where the compiler runs the code, figures out which path is a frequently executed path, and optimize it. But if the frequently executed path differs from the frequently executed path, if the frequently executed path when you actually run the program, optimized program, differs from the frequently executed path that the compiler thought was frequently executed to optimize the program, then these code optimizations may not actually provide benefits. In some cases, they may hurt performance, but compilers also are very careful in figuring out when they may be wrong. So they actually try to optimize the code in a way, if they're not sure this profile is not going to be very accurate, they try to actually be less aggressive in the compiler optimization. So people actually realize this problem, and they actually do a lot of work to avoid profile input set representativeness issue. You cannot avoid it completely, of course, but you can take some caution to fix that issue potentially, right? And of course, a dynamic code optimizer figures this out, meaning it optimizes the code, and dynamically, while running the code, it adds some checks. How often did this frequently executed path actually was not the frequently executed path? And if enough times it was wrong, it goes back and re-optimizes the code, right? Based on the changes in the dynamic execution. So if you have a dynamic compiler, you can adapt to these at, of course, compilation overheads that come at runtime. For this very reason, hardware designers, if you're designing the compiler and the hardware together, hardware actually can be designed to help the dynamic compiler. Hardware can actually keep some counts, do some profiling internally, and share that with the compiler, saying that compiler, you did something wrong, potentially, right? So you can actually co-optimize the hardware and the software together so that you keep compiling the code, but the hardware is profiling the code internally without actually software overhead, and they're communicating with each other so that the entire execution becomes better and better. So if you look at, for example, Transmeta, that was the vision and that they tried to implement. And that's true for the dynamic code optimizer at NVIDIA, for example, or Apple. So it's good to keep this in mind. If you're designing software and the hardware together, you can do a lot of interesting optimizations. Okay, so let's jump into systolic array architectures. But before we jump into that, I should say this because we work with a lot of bachelor students and they do a lot of interesting work. In fact, some of our papers have people who contributed in bachelor studies. So if you're interested in doing research in the areas that we work on, feel free to email us or talk to us. You can email me, CC Mohammed, with your interest. You can also take the seminar course and our more advanced computer architecture course. Of course, doing the readings helps. But basically, the key over here is talking with us. If you're interested in doing research at some point, of course, taking this course is a very good beginning. And if you enjoy it and if you actually do well in the concepts, etc. So there are many exciting projects, and we welcome everyone in general, all over the world. It doesn't matter if you're a bachelor student or a PhD student, but of course, with a PhD student, you have more background probably. But we do a lot of work on many topics, which I'm not going to talk about, but some new execution paradigms like in-memory computing is very exciting. We may talk about that later. But everything essentially we touched on in this class and more, let's say. Some of you may want to do a thesis at some point, and we offer bachelor's theses also. If you go to this page, you'll see some examples, but don't think that that's comprehensive. That page doesn't get updated very often because we're too busy doing research. So if you're really interested in doing research in these general topics, just contact us, even if a topic may not be listed in that page. And this page over here is our publications. Okay, so I would also maybe publicize the bachelor's seminar. If you're interested in these topics, again, I would suggest taking the bachelor's seminar course next fall or later. Essentially, this is a rigorous seminar on reading papers and presenting them and reviewing them and discussing them. And we emphasize a lot critical thinking and brainstorming on cutting edge as well as some really old papers. For example, the topic that I'm going to discuss, systolic arrays, was presented by one of your fellow students a few years ago. And that fellow student did his bachelor's thesis with us. He actually worked on some in-memory computing paper, and that in-memory computing paper got published at an ASP+ conference in 2021. I think it's called SIMDIAM, you can look it up. So he actually did a lot of very interesting, exciting early work based on this development, and he's a co-author of the paper. So if you're interested, you can take a look. That's just one example. There are many examples. Okay, so you can look at the link over here also. And this is our group, so you can learn more about us also by going to our website, looking at our newsletters. So we release a lot of these newsletters almost every year. And you can see that based on last time prediction, June 23, July 24. So the next one should be August 25, I guess. Let's hope so. Okay, so you can also learn more about our research through videos. Okay, and we're proud of our PhD, postdoc, and other alumni. Not everyone fits here, but a lot of people who get their PhDs and postdocs, and also masters, they have become thought leaders in academia as well as industry. And you can find more information about them online as well. So you're an ETH student, you're at a privilege level that's higher than, let's say, outsiders. So if you're interested in doing this, you don't need to apply because you're not coming from outside. We know you better, probably. We can talk to you directly and we can discuss with you. So talk with us. But if you're an outsider, meaning you're not here taking the course in person, it's the best way for us to get to know you is by you applying. Okay, with that, let's say brief advertisement, we can move to more execution paradigms. So basically what we're going to do is we're going to cover systolic arrays. Hopefully we'll cover everything, but hopefully we'll cover the basic important things. And I'm not going to cover decoupled access executes because it's a very short paradigm, but we're going to release a premiere of like a 10-minute lecture. If you're interested, you can look at it. And next week, well, rename next week, we're going to start SIMD processing, vector and array processors, GPUs, which are clearly extremely important today. So these lectures are going to wrap up the essentially different execution models that people have developed over many years. This doesn't include some of the execution models that we will talk about after we cover memory, like processing in memory. All of these are actually very processor-centric execution models in the sense that you have processor, you have memory. Memory's job is to just serve the needs of the processor. Processor says load, memory says yes, sir, here is your data. Processor says store, memory says yes, sir, or yes, ma'am, and here's I stored the data. Memory cannot speak. Processor says everything. So if you think about this as a very unfair model, and also a very imbalanced model, in the sense that memory cannot do anything other than obeying what the processor says, right? So all of these models are like that. But there's a very different way of thinking about systems where memory has a say. Processor says, okay, memory, can you do this for me? I have a function. Can you execute this for me? And the memory says, yeah, I can do that for you. So you don't need to do. You can execute the function that you can really execute, and I execute the function that I'm really good at executing. Because that function requires a whole lot of data. And in the processor, you execute the functions that require a whole lot of computation, not a lot of data. So that's the notion of memory-centric paradigms, which is processing in memory, for example. You put computation inside the memory devices such that memory devices are a lot more intelligent, and they actually take part in the computation as opposed to saying yes, sir, yes, ma'am all the time, right? So that's the idea of processing in memory, which is not here, but we may talk about it as, and this is something that's unfolding right now, and we're doing a lot of research on that topic to enable it. so that maybe 10 years later, it's taught in classes like this, and we're free of just this processor-centric paradigms, but we can be much more memory-centric. And just to give you one more motivation for why we're doing this, because there's a huge data movement problem. You'll see that in later lectures. And also, if processor-centric is very against nature, right? If you think about how brain does computation, in the brain, memory, communication, and processing is all meshed together. There's no huge distinction like what we have in our systems today. You don't move the data huge distances so that you can actually do processing in the brain. Okay, that's just to give you some different motivation. Okay, but now let's go back to processor-centric, but a very different processor-centric paradigm, systolic architectures. This was developed by H.T. Kung. Well, he was a professor at Carnegie Mellon University, where I was from, actually. I was a professor at. So this paper is a very highly recommended paper that talks about the systolic paradigm. And I was teaching these lectures. I introduced these lectures at CMU because they were not being taught. So I thought this is a really important paradigm. It has to be taught. It's very principled. And it's going to make its way to real systems at some point. 2009. Still 30 years like after H.T. Kung developed this paradigm. And now that you're listening to it in 2025, I can say it has made its way in a major way to machine learning accelerators because it's a very principled approach and it makes sense. So it's good to believe, it's good to have some fundamental principles. Even if it's not employed anywhere today, it may be employed somewhere tomorrow. So it's good to always have that mindset that is open. Okay, so I'm going to also recommend these papers. These are from Google, where they actually use systolic arrays to implement matrix multiplication in a very efficient way. So that, a lot of machine learning is matrix multiplication. And they actually employ this in all of their data centers as well as edge devices. So it's very cool that this sort of architecture has made its way. Next week, we're going to talk about GPUs, which is another architecture that has actually been very popular. But patience for that. Okay, so systolic arrays. Systolic arrays are on the special purpose end of the spectrum, right? This is, if you think about CPUs, VLIW, Superscalar, out of order, they're all on the general purpose end. We've been talking a lot about this general purpose paradigm. And you've seen this slide before. General purpose means you can execute any program. It's easy to program and use, but unfortunately, it doesn't get the best performance and efficiency on any program. On machine learning, it's okay, but it's not as good as something that you specialize for machine learning, for example. That's true for video, etc. So we're going to talk about GPUs next time. You've been programming FPGAs. You could argue the order, etc. over here. I'm not going to do that, but they're also special purpose machines designed specifically for some applications. Like the most special purpose machine is where you take a program and don't do anything but burn it into the hardware, meaning burn it into circuits. Do what the program does and you make sure the circuit is doing exactly that and nothing else. So that's an application-specific integrated circuit, very inflexible. So, but it's extremely efficient and high performance for that particular piece of the program, right? So it's usually difficult to program and use, and it's inflexible, limited set of programs. Normally, people don't do that as much today because they need some flexibility, but they could actually customize the circuit so that it can do matrix vector multiplication, for example, right? Some important kernel as opposed to a full program. But still, that's special purpose, right? It cannot do everything very well. So we're going to look at a special purpose system today. VLIW was a general purpose paradigm. Systolic array is going to be a very special purpose paradigm. Okay, it's an execution model, actually. Systolic arrays are an execution model. They implement what is called systolic computation, as we will see. And it's a very general computation, but your program needs to be written that way. This is different from the von Neumann model, different from the data flow model. So we're going to forget about any of that. We're going to have a different model right now. But it's going to be more specialized than what can be enabled with von Neumann and data flow. So they were initially designed as special purpose accelerators, and they actually remain as special purpose accelerators. And the main reason they were designed is actually convolutions. We're going to define convolution. How many people know about convolutions? Okay. Where have you seen it? And CNN. Okay, yes. Convolutional neural networks, for example. Yes, convolutions are there before CNNs existed, actually. Convolution is an operation that you do on images, for example. But yes, CNNs made it popular, and I'm going to talk about that also briefly without going into a lot of detail. But convolutions, filtering, pattern matching, special purpose matrix vector computations and image vision processing, signal processing, pattern recognition, these all do convolutions and different filtering type of operations. Convolution is actually a filtering operation, as we will see soon. Today, they're used heavily in machine learning, systolic arrays. These are specialized machine learning accelerators. And their general execution model can be generalized, as we will see later in this lecture. It can be generalized to a way of thinking about programming, actually. Okay, so let's talk about the motivation. We're talking about 1970s. The motivation of H.T. Kung was to design an accelerator that has simple, regular design, simple hardware. This is what it shares with VLIW, for example. Keep number of unique parts small and regular. High concurrency, we want extremely high performance. At that time, energy was not a big concern. But today, energy is a huge concern, and that's why Google's TPU has these systolic arrays, not just performance. Balanced computation and I/O bandwidth, meaning, as we will see soon, H.T. Kung realized, and he did a lot of work on this topic, and this is one of the reasons why we work on processing in memory as well. But he said that if you have a processor that just keeps doing load, store, load, store, load, store, you're not balanced. Meaning you have a lot of computation power in the processor, but memory is very slow and has low bandwidth. So you're basically bottlenecked by memory. So let me design a hardware accelerator that's not bottlenecked by memory, or balances the computation bandwidth and the memory bandwidth. And we will see that in a picture. So the idea is very simple here. You start with a processing element. This processing element could be very, very simple, as we will see. It could do just multiply and accumulate, multiply and add. Because we're going to be special purpose, right? We're not going to be general purpose. But it could be a general purpose processing element also, as you generalize the paradigm. And then you replace that processing element with a regular array of processing elements. It could be one-dimensional array, two-dimensional arrays, multi-dimensional arrays, etc. We're going to start with one-dimensional. And you carefully orchestrate flow of data between the processing elements, such that they collectively transform. They read from memory one piece of data, and the first processing element takes it, transforms it, passes to the next one. That one takes the transformed data, does something to it, does some operation, passes to the next one, and you keep passing the data between the processing elements. Eventually, you write it back to memory. Okay? So it's kind of systolic in that sense. So the benefit of this is you take a piece of data, you read from memory, and you do a lot of computation on it before you write it back to memory, as opposed to doing a single processing element, load, store, load, store, load, store, load, store, load, store. So that's the idea over here. And this is a beautiful picture from H.T. Kung's paper. Basically, he says that this is a processing element. It could be, again, as simple or as complex as you imagine it. But if you're doing, you're fetching one piece of data over here and then operating on it and writing it back to memory, you're limited by the memory bandwidth over here. Your computation is basically limited by how fast you can get data from memory. But if you take the same data element, do some computation, transform it, pass it to another processing element, do some computation, transform it, and pass it to another processing element, and keep doing that, you can actually increase the operational capacity because you're not bound by memory bandwidth anymore. Make sense? Basically, you're still bound by how fast you can get the data from memory, but you're doing more on the data that you fetch from memory by chaining these processing elements together. And you can see that this number is 5 million operations per second with some assumptions. Here, because you have 6 processing elements, you can do 30 million operations per second. Okay, so this is a forward-looking approach, as you can see. And why is it systolic? Because he basically gives the analogy, memory is the heart, data is the blood, and processing elements are the cells. Memory pulses the data through the processing elements, and eventually data or blood returns to the heart, right? So you keep circulating this blood. Okay, that's analogy at some point breaks down, but it's a good analogy. That's why it's called systolic. So basically, data flows from the computer memory in a rhythmic fashion, passing through many processing elements before it returns to memory. And I already said this, similar to blood flow, different cells or processing elements process the blood. Many veins operate simultaneously, similar to a body, right? And this can be many dimensional, just like veins can be many dimensional. So there's no reason this could be linear. This could be two-dimensional. As we will see, in fact, for matrix multiplication, you want two-dimensional arrays. But you could actually chain these arrays, as we will see also. So it's actually a fascinating paradigm. So why did he do this? Basically, he was trying to design special purpose accelerators with the requirements that I said earlier. Simple design, high concurrency, balancing I/O and computation bandwidth. So I've already said a lot of this over here, and this is the picture. So you may say, okay, this looks like pipelining. In a sense, yes, you're pipelining these processing elements. That's actually true. Another way of thinking of this is pipeline parallelism. You're exploiting some pipeline parallelism. But it's not the same as a pipeline that we've seen in earlier lectures. It's very different, right? Here, the processing elements are doing the same computation, for example. You're not pipelining instruction execution, essentially. These are individual processing elements. They could actually be individual cores if you generalize the paradigm. When we generalize the paradigm, we'll talk about that. An array structure can also be nonlinear and multidimensional. It doesn't have to be linear like this. You could have actually a two-dimensional array. Processing element connections can be multidirectional, different speeds. So now it doesn't look like pipelining anymore, clearly. And processing elements can have local memory and execute kernels. So each processing element can be executing multiple instructions, for example. We're going to start very simple. We're not going to do that yet. But essentially, the huge difference from pipelining is the pipelining as we developed, I don't know how many lectures ago, 5, 6, 7, 8. Hopefully it's ingrained in your thinking right now. How is this pipelining? You basically take an instruction in pipelining and divide it into stages, right? Different stages execute different pieces of the same instruction. Here you're doing the same operation on different data elements, and you're changing the processing elements such that the operation that you're doing on the data is based on transformed piece of data, and you're not directly connected to memory. Okay, so hopefully that's clear. Now let's talk about some systolic computations, and I'm going to also diverge and talk about neural networks a little bit. This is not going to be a neural network course. If we talk about neural networks in this course, it's not going to be ending, but I'm going to motivate it also. So convolution, it's a very fundamental operation. It was there long before deep neural networks. It was especially used in filtering, pattern matching, correlation, polynomial evaluation for especially image and vision processing tasks used in robotics, for example, right? And if you're designing a robot, you need image processing, you need vision processing, and you want that to be very quick and very fast, and convolution was the fundamental operation. Machine learning more recently came about, and well, at least the modern form of machine learning, neural networks, more recently came out, and we're going to have a story about that also. And you get up to hundreds of convolutional layers that do a lot of convolutions, essentially. These operations are very common in neural networks. What is a convolution operation? Essentially, it's a filtering operation. You have an input sequence, x, a vector of x, and you have some weights, vector of w, and you compute this essentially polynomial evaluation, yi, you compute a vector of y's, y0, y1, y2, or based on this notation, y1, y2, y3, y4, etc. And each y is computed this way. Again, you don't need to memorize exactly how it is, but this is based on mathematical principles, etc. But this is the computation that we're going to try to accelerate. In the end, you can accelerate other computations also, but this is a good example. And if you look at a convolutional neural network, this is a picture of LeNet, not so deep neural network, but it's one of the deeper neural networks when people started developing deep neural networks. It's 5 stages, as you can see. And basically, whenever you do some image processing, to recognize part of the image, you apply some filtering operation to it. So there's some convolution that you do, and then you basically do a lot of convolutions to try to figure out what this is, and then you do some sampling, more convolutions, more sampling, and then do some computation, and eventually you say, oh, I think it's an A. Right. So this is basically how neural networks work at a very high level. We're not going to go into the details of it. But this is essentially a convolution operation on an input versus output. So if you look at this input, this is one input, for example, to a convolutional layer. It's a 2-dimensional input, as you can see. And basically, this gray box over here is the filter. You apply this filter to all of the parts of this input feature map so that you can produce an output feature map. This is what this is doing, is the convolution. And this convolution kernel can be different based on its values, depending on the weights that you use, for example. And in neural networks, you learn these weights, so you try to figure out what are the best weights to actually use so that I can actually identify this image using multiple different layers. Okay, so basically what this is doing is, for example, as it moves through the input, that's called an image, because this was developed for images initially. It basically does some computation of this 3x3 kernel to the 3x3 portion of the input, right? And then it generates every single element of the output, as you can see. Hopefully that's clear, right? This is basically that polynomial that I showed you put into a picture, okay? Without showing the calculations exactly. Okay, and this is a maybe nicer one. And you can actually, essentially you're doing multiplication of these kernels with the input layer so that you get an output layer. Now you can see that there's a matrix multiplication going on over here. Okay, so if you're interested in this, there's a lot of information clearly on neural networks. Jan LeCun, one of the pioneers in this field, has his webpage that talks about how these work. I'm not going to talk about how these work at this point, but essentially this is a very fundamental operation that is used in many layers. And you could implement this in different ways. Essentially, you could implement this convolution layer using matrix multiplication. And that's what we're going to try to accelerate a little bit. So if you look at this picture, these are the input features, input matrices. These are the convolutional filters with the weights, X, W, and then we want to compute the output features. So what you do is you take pieces of the input feature, like this is 2 by 2 elements, and then you multiply it with this filter, and then you take this other one, multiply it with this filter, and you take this other one, multiply it with this filter, and then that forms an element of the output. Again, this is the definition of the computation pictorialized. And if you do the calculation, you will see that once you multiply this matrix with this matrix, the result is 2, 2, 2, 7. I hope I got that right. And once you multiply this matrix with this matrix, you get the result. You take the dot product, basically. Sorry, I should say dot product. You take the dot product of this with this, you get 7, basically, because you multiply this one, this 2 with this 1, and this 1 with this 2, and this 1 with this 2, right? And you do the same thing over here, and you get an additional 3, and you do the same thing over here, you get an additional 2 over here, so you should get 12, and this says 12. I can verify the rest was just simple computation, right? So this is one way of doing it, and we're going to implement something similar to this. But you could also lay out this filter in a horizontal vectorized fashion. So this filter right now is collapsed into a vector 1, 1, 2, 2, as you can see, and then 1, 1, 1, 1, and then 0, 1, 1, 0. And then you also put the other filter over here. Now this looks like a matrix. It's really a row of different vectors, weights. And then you multiply it with the input features that are unrolled. Essentially, you can see that this belongs to this. No, actually, that's not correct. Essentially, you take some of these over here, 4 of them over here, unroll them, and this collectively is this collectively is here, and this collectively is here. And then you basically now have 2 matrices, and you multiply these 2 matrices together. And multiplying 2 matrices together is really, you multiply this row with this row, so that you get a dot product of those, and you basically do it for all rows and columns. So you can see the same thing done in different ways. So this is where GPUs will be very useful, very good, because this is really, you do the same operations on multiple different data elements with huge vectors. We will see that with vector processing tomorrow, not tomorrow again, rename tomorrow to next week, next week. And we're going to see how this computation is done using systolic arrays today. But the realization is that you could do these very efficiently and at high performance with GPUs. And just to give you a history of why this is really important today and why actually courses matter in universities, some people, some smart students who took a parallel processing course programmed GPUs at the University of Toronto. And these folks basically said, oh, we can accelerate neural networks using these GPUs. And they started training a deep neural network with 1.2 million images, and they participated in this ImageNet competition. And they won the ImageNet competition, and they wrote this paper, which is probably known. How many people know this paper? Okay, a lot of you may know this paper. If you know this paper, that means something. Essentially, this is the first paper that showed that with a deep neural network, you can classify images or identify images much better than what was previously done before with shallower networks, a lot shallower networks. But the reason they were able to do this was that actually they learned how to use GPUs and how to actually translate a neural network to a GPU and optimize it. Okay, so that's a nice story. I think I like it because it shows the power of smart people applying what they've done to a totally different domain that's being taught than what's being taught. And then later, Google developed its own, let's say, GoogleNet model. This was called AlexNet because the first author is Alex. And you may realize some people, Jeff Hinton, for example. Say again? Yeah, that's good. Oh, yeah, okay, you realize that also. Yeah, see, it's famous for multiple reasons, let's say. Okay, but Google later developed their own deeper neural networks, and later other people developed deeper neural networks from Microsoft, for example. But just to show you, before this AlexNet paper came about, the competition had a lot of error rate. So these are images, basically, that are fed to you know these images. You basically try to identify these images automatically using some mechanisms, right? Using some software. Before, with shallow neural networks, the best approach had 25% error rate. And these folks essentially revolutionized the thinking by having deeper neural networks, and there was a huge reduction, like almost 10-point reduction in the error rate. You may say 10-point does not matter, but this is what started all of this neural network, let's say, revolution, sometimes hype also, but there's clearly a benefit over here, right? And later, so 10-point matters. Don't underestimate 10 points, right? And it's less than 10 points, actually, if you do the calculation. Okay, so and then later people, this is similar to branch prediction, right? Little advances actually matter a lot, as you can see. And later people developed many layers, and you can see that this is 2014. This was the first convolutional neural network. The previous ones were not doing convolutions. Okay, you can read about them also. But for example, this one has 52 layers. This is 2015. And this was the first one that actually outperformed human level recognition of images. You could argue that, okay, these images are limited data sets, and there are other more difficult images humans can do better, but this is limited by the data set. So that's why convolutions are important, because that they found their application, for example, in the modern world in 2012, let's say. And if you look at a neural network today, the blue parts are the convolution layers, for example. That's AlexNet. LeNet is actually simpler. It has 2 convolution layers, but as you add more convolution layers, you can actually get more accurate, and that's what people have shown. And here you can see, for example, 152 layers. A lot more computation, of course, right? And a lot more training, right? Okay. And we're not talking about LLMs yet, but that's the subject of a different thing. Okay, now let's go back to this convolution and how it's done using systolic arrays. I've already talked about everything. Now we're going to actually execute this polynomial evaluation using a systolic array. Again, we're going to 1970s. H.T. Kung's paper, one of the papers, did this. And this is a systolic array over here. Basically, what we're computing is, assume that you have 3 x's. The vectors are of length 3. Y1, Y2, and Y3 are computed this way. Weight 1 times x1, weight 2 times x2, weight 3 times x3 added together. And then Y2 is computed this way, and Y3 is computed this way. So H.T. Kung said this can be done with this chaining of processing elements and carefully orchestrating data such that where inputs come at the right points so that you can actually do this computation, and then outputs go out at the right point so that you can actually capture the result that I need. So let's take a look at that. We're going to start with a very simple processing element that looks like this. Weights are hard-coded, let's say put inside there initially. You could also program them. But what this processing element does is it has 2 inputs, 2 outputs, as you can see. X input is coming from the left, and the X output is going to the right. And X out is equal to X in. Essentially, the processing element's job is at the beginning of cycle takes X out, at the end of the cycle gives it to the next element. Right? You're passing the data essentially. Input data is X. And the outputs are going this way. So essentially, Y output gets input at the beginning of the cycle, and then Y output gets output at the end of the cycle, such that the next element gets in the next cycle. And essentially, Y out is equal to Y in plus weight times X in. So it's a multiply and accumulate. You multiply the weight with the X in and add to it Y in, the output coming from the previous element, previous to you, and then output the data to the left. So it's doing a multiply and accumulate, right? It's multiplying the Y input with a weight and then accumulating it and then giving it to the next element. Okay, now we're chaining, let's chain these elements. So we have 3 of these elements here. One of them stores weight 1, the other stores weight 2, the other stores weight 3. And we're going to orchestrate the data flow, input data flow like this, such that you basically pump in X's. At some point, X1 reaches here, and then there is some empty slot over here. X2 reaches here. And then basically you separate the X's such that an X is supplied every other cycle, okay? And then the outputs come this way, Y1 comes here. So basically when X1 reaches here, Y1 also reaches here, and that processing element gets triggered. And what it does is it computes, as we said, here you basically don't pass it anywhere because they get dropped, so you don't use this output because there's nothing else after this point. but y1 is computed by multiplying x1 with w1 over here. And then the next cycle, y1 goes here, and it's x1 w1. Right? And the next cycle, you have x1 w1 over here, and then x2 moves here. And again, y1 becomes x1 w1, which was coming before, plus x2 w2, right? And then next cycle, y1 moves here, and then x3 moves here. So now, again, you hopefully got it, but basically, the multiply operation is y3, x3. You add to it whatever you computed as y1 before, which is wx1, x1, and w2, x2. So eventually, y1 goes out here, computing this thing, okay? So, and you can also think about what others are computed over here. For example, when x1, so y2 comes later over here, and you actually do similar computations on y2 as well. Okay. This is not shown over here, but you can imagine y2 being pumped over here. We're going to see another example that does matrix multiplication. Hopefully this is clear, right? This is beautiful. Inputs are coming in one direction. While the inputs are coming, processing elements are doing the operation, and outputs are going in the other direction. There's no instruction here. We got rid of all the instructions. Forget about all of the MIPS, x86, there's none of them. This is a very specialized processor for doing convolutions. Is this beautiful? Yeah, so you can see now, the instructions are gone, all of the overhead is gone. You can focus all of your effort to doing convolutions. Right? And that's the power of specialized hardware, as you can see, right? You don't waste any of your power or computational power or energy on doing anything else but what you really want to do, assuming this is what you really want to do. Now feed to it something else, like, I don't know, a database access. Good luck, it's not going to execute that for you, right? Okay, so hopefully this is clear now. This is, again, from the paper. And later, in some other figure in the paper, H.T. Kung shows that you could actually get a higher throughput by implementing the multiplier and adder separately, as opposed to doing a fused multiply and add operation. I will not talk about this in detail, but this is based on pipelining principles that we have seen. You could actually get higher throughput, a little bit extra cost, because you need to actually latch some of the intermediate results. When you do multiply, for example, you latch the result and then you do the add. But this actually amplifies the computational power of the systolic array with some additional hardware cost. That's the idea over here, but I will not go into this. The paper is beautiful, so you can read more. Okay, so basically, hopefully it's clear that to be able to, for this to work, you need to figure out what your computation block is, and you also need to carefully orchestrate the data when data elements are input to the array, both inputs and outputs. Right? And when the output is buffered, when you actually capture the output at the end. So this is important. This gets more involved when things become more complex. When array dimensionality increases, for example, as we will see, but for matrix multiplication, it's going to be okay. When processing elements become less predictable in terms of latency, for example, if they're not doing just multiply and accumulate, but they're doing some memory access, as we will see, they're going to be very difficult. But let's take a look at matrix multiplication first. So another example of systolic computation. This is exactly the reason that's used in, for example, TPUs. If you want to multiply two 3x3 matrices, matrix multiplication is you take this row, take a dot product of it, and store it in B00. You take this row, take a dot product of the second column, that's 0, 1. This row with the third column, that's 0, 2. Okay, hopefully you know that. We're going to use this processing element. Essentially, R is the result that we're going to accumulate. And this is, again, a multiply and accumulate. You basically multiply M and N and add to it to R. Initially, R will be 0. And P will be passing M from left to right, and Q will be passing N from top to bottom. And this is a systolic array that does this computation, assuming these processing elements. So it's a 3x3 matrix at the end, and the results will be stored in R of each element. And this is how we supply the data elements. Inputs, A0s, B0s, A1s, B1s, etc. And this is the time at which each element goes into the array. So let's take a look. At time 0, A00 is here, B00 is here. At that time, you compute A00 times B00, store the result over here, right? And then pass A00 here, and then B00 goes down here. So initially, you give 0 over here because you want this processing element to compute something when A00 comes over here, right? So you orchestrate the data such that the data that's coming for the next row arrives when what you need from the next column arrives over here, right? So when B00 arrives here, A10 arrives here, and you multiply A10 and B00, and that's what you exactly want, right? A10, B00. And then you basically keep accumulating results over here. So hopefully it's clear. I will not go through the entire thing. This is something, actually, this was one of the homework questions for you to study. I will let you figure it out, but it's very easy to figure out. As data moves in, this processing element does computation. It adds to what it has accumulated before, whatever it comes. For example, we had A00, B00. When A00 moves here, B00 moves here, B10 moves here, A10 moves here, and you add to A00, B00, which was stored here, A01, B10, right? And that's exactly what we want. A00, B00, A01, B10. And then next cycle, A02 comes here and B20 comes here, and you add to whatever was stored over here, A02 times B20, which is really dot product of this vector with this vector, right? That's beautiful. And you can convince yourself that everything works as expected, and in the end, in these cells, you get C0s that are calculated mathematically with matrix multiplication. Okay? Okay, so that's beautiful. You could do more. You could have actually multi-dimensional systolic arrays, which is interesting. I'll let you read the paper if you're interested. You can combine systolic arrays together. I will go through this relatively quickly also, but essentially you can form more powerful systems. For example, this is an example from the book, not from the book, from H.T. Kung's beautiful paper. You have a systolic array over here. Again, orchestrate the inputs. It's capable of producing least square fit to all the data that it's seen. You can think of it as a sensor, for example. Sensor is getting a lot of data from something, from some camera. It's trying to basically figure out what it is. And if least squares fit is what you want to do to that data, maybe you can actually approximate that function that you're seeing, right? Whatever the data elements are. You could do, for example, anomaly detection using these very specialized circuits as opposed to using CPUs or GPUs that are heavy-handed, assuming you can design these circuits. So, and you can design them. You can see that sometimes you may need to add some buffers, etc., so that you can communicate. But these are beautiful, essentially. If you want to specialize systems that are very energy efficient, you can do that by making the systolic array bigger, more powerful, etc. Okay, let's talk about advantages. So a big advantage, this is very principled. It efficiently makes use of limited memory bandwidth, balances computation to I/O bandwidth available. Specialized, so you can actually be very energy efficient and very high performance at the same time, because you get rid of a lot of the overheads. No instruction fetching overhead, no instruction decoding, no instruction, nothing like that. You actually reduce the memory overhead also. Control overhead is gone. You're spending most of your effort on data processing. Okay, so essentially efficiency, simple design, high concurrency, and performance. So you're doing more with less memory bandwidth. Downside is also specialized. Clearly, this is not generally applicable because computation needs to fit the processing elements, functions, and organization. So you can generalize this though. So you can actually have each processing element to store multiple weights. Weights can be selected on the fly. You can actually do very adaptive implementations. Let me give you an example quickly. If you take this further, each processing element can have its data and instruction memory. And data memory can be storing some results, some constants. And if you actually generalize the model, each processing element can be its own core, right? It could be a core that's a general purpose core, right? Now this becomes like a programming model of the cores. And this is called a pipeline parallel programming model. I call it stage execution. And I'll give you an example of this. So basically, for example, it's a very general model. You can take a loop. You can divide it into 3 stages, let's say, for some reason. Stage A may be doing something. Stage B may be doing something else. Stage C may be doing something else, and they may be operating on similar data sets. Stage A is always operating on this data. Stage B is always operating on some other data. Stage C is always operating on some other data. You partition the program, and in a single processor, you may execute them like this: A0, B0, C0, the first iteration; A1, B1, C1, the next iteration; A2, B2, C2, the next iteration. But with 3 processors that are chained together in a systolic manner, P0, P1, P2, P0 starts with A0, and then it moves to A1. Well, and then at the same time, P1 does B0, and then it moves to B2. And at this point, you can see at this time, P0 is executing A2, P1 is executing B1, P2 is executing C0. assuming dependencies allow it, of course, right? And this is one way of parallelizing programs, which is a very powerful way, pipeline parallels. Now, this is a computation model now. It's not just a hardware model, it's really a computation model of programs, and this is systolic computation. And this is also called pipeline parallel, so at some point, pipelining and systolic look similar. So I've already given you this, so let's take a look. You can actually have cores. Threads can execute stages on different cores. Cores can be specialized for the computations that execute on them. That's key. So these could be general purpose cores, but it could be very, very specialized for ABC as well. Let me give you an example with something that's actually done. So video processing is one example. You take pieces of a video, do different stages on it, and then output. And if you have lots of videos coming in, which is the case in YouTube, for example, you're doing this on huge data sets. And if you divide it into cores like this, you can be extremely efficient. And then you can design a hardware accelerator for video encoding and decoding, which Google does also in a pipeline parallel manner. Okay, this is where we will stop. I guess next week, we're going to pick it up. Probably from here, we'll talk about TPUs, and then we'll talk about GPUs. Hopefully, you'll have some rest and a good time during the Easter break. Have a good break. I'll see you soon.